So in this section, we're going to do something that we've kind of done already. All right, we've done this. We've literally used this formula, except we've used it in a different context. Earlier in the year, we talked about bodies that have mass, and mass warps the space around them, and as a result, it creates a gravitational pull. So we talked about how even if that bottle right there in front of Mike, even though it doesn't have a lot of mass, it has a gravitational pull on him, on the objects around him. You have a gravitational pull on everything around you, on this roll of tape, on this scissor, whatever you want to think about. You always exert a gravitational pull. Why is that again? Because you have a mass. Now we're going to talk today about, well, what if you have an electric charge? So instead of it being a particle with just mass, it's a particle, all particles have mass, but it's a particle that's also charged. So we're going to use the same rule, though, that we did with gravity. Okay, we're going to use it's really the same law, except with a new constant. Instead of mass, we're going to use charge. So let's dive right into this. So let's take a look at this formula here. Do you see how I'm talking about how it's the same rule? Who remembers the Newton's law of gravity? Not Fg equals mg, but the longer one. The longer one, Newton's law of gravity. You could look at your formula sheet, or if you memorize it, just tell me what it is. Anyone remember this? It was Fg equals, and not the one that says mg. I mean the longer formula that we had earlier when we did Newton's laws. Marilyn, what do you got?
6 point. Was it that? It was a variable.
Good.
Times something.
All right, you're halfway there, or a quarter. Good. So this was the formula right here from earlier in the year. Look at the formula we have now. It's really the same thing. Instead of g, where g was the gravitational constant, k is called the Coulomb constant. It's the electrical constant. That's all it is. Instead of a gravitational force constant, this is the electrical force constant. Fe stands for the force due to the electric field. This is the force due to the gravitational field. So these are really the same thing, except instead of a mass, what do I have now? Q1 and Q2. Those are the charges on the two particles. Again, Q1 and Q2 are the charges on the two particles. Just like with the law of gravity, both objects have to have mass, right? You can't have gravity between two objects if they don't have mass. Can you have an object without mass? No. Every object has mass. Everything, even an electron that is very, very, very minimal mass, it still has mass. So both of these objects had mass. Well, in this formula, both of the objects will have a charge, some sort of electrical charge. And that's from last lesson. Remember that was measured in coulombs? We talked about the charge on an electron was negative 1.6 times 10 to the negative 19. The charge on a proton, positive 1.6 times 10 to the negative 19. These values that I'm spitting off right now, those were from section 19.1. And those were measured in coulombs. Coulombs is the unit to measure charge. Just like kilograms was used to measure mass, here we use kilograms. For Q1 and Q2, we're using coulombs, the measurement of charge on the particle. R is similar in nature to this. It's the distance from center to center. Okay. Now, with massive, large objects, we also incorporated the radius when we were looking from like the center to center between, like, for example, the moon and the earth. We incorporated the radius because it was a big value. The radius of the earth is a large value. With these problems, we're going to see that we're really not going to have to incorporate that extra radius because of the fact that the radius of an electron compared to the distance from the nucleus is so insignificant it has no effect. So this r, although being distance from center to center, could really be thought of as the distance between the two charged particles. But these formulas are really the same thing. I want you all to see that. This is what, remember I always talk about like the beauty of physics? This is where the beauty of physics comes in. Two completely different things. One, gravity. One, electric fields. Related with the same formula. The exact analogous nature of the formula. Yeah, the force is directly related to the charges, or the force is directly related to the masses. Both properties of the particles. What is it indirectly related to? The distance away squared. The distance away squared. One of them had gravitational constant. One had Coulomb's constant. Okay, so again, new formula, but it's really the same thing. All right, let's press on to the second slide here. With that in mind, let's go ahead and use the following information. Let's calculate the electric and gravitational force. So we're going to go back to Newton's laws and use that formula we just wrote down to calculate the gravitational pull. But let's also calculate the electric pull between a proton and an electron. And we are specifically talking about the hydrogen atom. Why? Why the hydrogen atom? What do you know about the hydrogen atom? It has what? What does it have specifically about it? 0 neutrons and how many electrons? And how many protons? So literally, a hydrogen atom is exactly the scenario where you have an electron and a proton at a distance. Again, a single proton and a single electron separated from each other, well, that's just a hydrogen atom. The proton is really in the nucleus, but there's no neutrons, right? So this is really just a proton and an electron at a given distance. The reason I'm having you calculate both the gravitational and electric force is so that you can compare the two. So as much as you guys think right now, isn't gravity pretty heavy? It pulls you to the earth. It's pretty strong as a force. Turns out we're going to see in a little while that the electric force is really even stronger on a close proximity. Okay, the electric force is even stronger on a close proximity. So let's go ahead and use these two formulas. So the first formula, let's start with the electric force, the new one. The electric force is Kc, which is Coulomb's constant, Q1, Q2, over R squared. Now, Kc is a constant. Where do you think you're going to find it if you don't know what it is? Yeah. Okay, just like all the other constants, at the very bottom of the formula sheet, you have your constants listed. Now, Kc is easy to remember. It's 9 times 10 to the 9. The double 9 makes it pretty easy. So they're all, after you use these enough, you'll probably end up memorizing them themselves. Now, the Q1 and the Q2, though, we have to recognize that we're looking at the charge on a proton and the charge on an electron. They're the same. One is positive, though, and the other is negative. But remember from 19.1 that the fundamental charge, E, is the proton and the electron, one positive, one negative. So those are what go into place at the top, right here and here. Doesn't matter which is first. Start with the electron if you want. And then the proton. What kind of an answer am I going to get? What kind of an answer will I get for a problem like this? Yeah, I'm going to get a negative answer. And please don't let that deter you from your answer or make you think, oh, this must be wrong. This is one of those scenarios where we're seeing, and in your text, if you recognize, your text actually puts absolute value around everything to make it come out to be positive, and you can do that, that's fine. But you need to recognize that this force is attractive. Why is this an attractive force? Who can answer that question? Why is the answer that we get, the number in newtons, going to be an attractive force? Attractive. Think back to electric charges from 19.1. What did it have to do with?
The opposites.
Yeah. If you have a positive and a negative charge, opposites attract. What if they were both positive charges? What would these particles feel? Repulsion. Good. They would repel from one another. They'd feel a repulsive force, repulsion. So in this section, what you're going to notice, write yourself a little note. If there's only two particles, when we get to three particles, it's a little bit trickier, and we'll talk about that. But when there's only two particles, if you get a negative answer, it's attraction. But if both of these signs are the same, even if they're both negative, right? Two negatives make a positive. So if they're both the same sign, like two electrons, or if they're both the same sign, like two protons, that's a force of repulsion. So a positive answer here on the end will yield or will demonstrate to us that this is a force of repulsion if there was a positive answer. Our answer here will be negative again because we're looking at a force of attraction. What do we get? What do we get for Fe? And this is a point where you need to be able to do this. If you don't get the same answer as me, or you don't get the same answer as your classmates because you're not typing it in right, you got to advocate for yourself and come see me at some point in time just to even practice this with your calculator. Travis, what do you got for this? Okay, and it seems like a really small number because you're looking at orders of magnitude that were really small to start. These orders of magnitude, negative 19, are really small. So your answer is going to be relatively small in general, but it's good to recognize, though, that compared to gravity, we're going to notice something. Okay, so let's take a look. Did others get that so I can confirm? Yes? Okay. Let's take a look at the gravitational pull between these two objects. So we go to our old school formula from earlier in the year, from a ways ago. And we're just going to compare these two. So does anybody remember capital G? Anybody remember that constant?
6.67 times 10 to the negative 11.
Yeah, 667, 10 to the negative 11. 667, 10 to the negative 11. That's how I said it to you guys so that you remember it. It's not a hard one to remember, but if you forgot, it's on your formula sheet. 667, 10 to the negative 11. Now the mass of the proton and the electron are listed above, so we can write those down. The mass of the proton, doesn't matter which one first. Here's the proton. And the mass of an electron. All over the distance between them squared. Same number in the denominator. So again, forget the sign, please. Forget the sign that we're looking at. Just look at the answer and compare the two. So what do we end up getting? This is a long calculation. Please use your calculator properly. Don't use times in there. Use that capital EE symbol if you're like, what is he talking about? That means you need to actually ask. Or maybe just, YouTube, how to use scientific notation on a calculator. It's very simple to watch how to do it. We'll come see me. What do you get from the product of these over the denominator squared here? What does your number become for this one? I see 1, 2, 3, 4, 5, 6, 7 calculators out of about half the room. Come on, people. Second, and then there's like I think it's the comma. Yeah, the comma. And then it'll put a capital E on your screen. That replaces times 10 to them. The first one? Okay, that's fine. That's why I asked to verify. No big deal. If I look at my notes, I have a different answer. I have negative 8.2 times 10 to the negative 8 for the first one. Is that what you got when you squared it? So here what they both said. They said they forgot to square this denominator right here when they did this. So change this number. Okay, again, that's why I'm relying on you guys to check each other. Good thing you checked there. Negative 8.2 times 10 to the negative 8 newtons. If that's what we'll end up getting for that one. You got the second one? What do you got, B?
3.61
Times 10 to the negative
47.
47. And I did get that one. I'll verify that one. So here's what I want you to see. Forget the negative positive part for a minute. The only reason we see negative again is because it was a proton and electron, so they're attracting each other. But look at the numbers themselves. Although 10 to the negative 8 makes the electric force a rather small number, the gravitational force is on the order of 10 to the negative 47. This is a whole lot smaller than this number is over here. Again, forget the negative, forget the positive. Just look at the order of magnitude. This is a much larger number than this is, by a lot. Negative 47 versus negative 8. This is 46 zeros before you get to 0361.
When you say that if you get a negative number, it means attraction, does that mean the negative exponent up top, 10 to the negative?
It's this negative right here. Yeah. So the negative exponent, what does that really mean, Matt? Do you remember?
It means it's going out.
Yeah, it needs to move the decimal. How many spots? 8 spots this way. Or this time, look down here, move the decimal 47 spots this way. So this would be a decimal with 46 zeros, then 361. So still a positive number. Now remember, gravity, what's the answer always going to be, though? always going to be positive because mass, this is mass 1, mass 2. What's mass always? It's always positive. You can't have a negative mass. It doesn't make sense. Mass is the amount of matter that makes up an object. You can't have a negative amount of matter making up an object. So gravity will always be a positive, always. And gravity is always an attractive force. The electric force, though, can be either attractive or repulsive. And it's easy to see that, whether it's negative or positive, when it's a two-body system. The minute we have 3 particles, it's a little bit more tricky. All right? It's a good question. So again, if you want to write yourself a little note, I would be jotting down the fact that this means it's an attractive force. How do I know that? Well, it's a positive and a negative charge. Opposites naturally attract. Opposites naturally attract. All right, let's take a look at the second one. The second one, now, what I like to recognize here is that we did this problem already. We did it with 2 dump trucks. And I told you how much mass each truck had, and I told you the force that existed between the trucks, and your question was, find out how far apart they are. Well, it's the same thing here now, except now I've got 2 particles with charges on them, not a mass. So if I'm looking for the distance between them, and I'm told that they have a repulsive force between them due to some charges, I'm doing the same thing as the dump truck problem. Instead of it being 2 dump trucks, now here's 1 particle, here's the other. The question becomes, how far apart are they? How far apart are they? What's the R value? Well, we know that the first one, charge, is 50 times 10 to the negative 6 coulombs. The second one is 40 times 10 to the negative 6 coulombs. 50 times 10 to the negative 6, 40 times 10 to the negative. Where am I getting 10 to the negative 6 from? Suddenly I'm introducing that value. It's not given in the problem anywhere. Why am I writing times 10 to the negative 6? Why am I writing 10 to the negative 6? Same 2 hands, same third hand over here. Think, why 10 to the negative 6? Jack, go for it.
Because that would equal micrometer.
Very good.
Micro.
Micro is a prefix. Very good. Micro, the symbol as a prefix is mu. It's the same symbol as the coefficient of kinetic or static friction. But it means something totally different when it's a prefix. This is a prefix for the unit coulomb. Micro means 10 to the negative 6. Okay? Micro means 10 to the negative 6. Microscope? Microscope, what are you seeing? You're seeing things on the order of 10 to the negative 6 meters when you use a microscope. Now, with that stated, we've got Q1, we've got Q2. We know that the force between them is 150 newtons. How come I know this is true? How come I know that it's a positive 150 and not a negative 150? Yeah, it says here that it's a repulsive force. Not to mention, look at your charges. They're both positive. So I've got 2 positive charges at a distance away from each other. They're going to want to repel each other. If they're both positive, you get a positive times a positive. The force itself must be positive. So we jump right into that formula. Can somebody suggest a way of solving this nice and quick, nice and easy? Without even using numbers right away, let's make it easy and smooth and quick. What do you think? What do you think? Martha, go ahead. Go for it. And then how do you get rid of FE? So what should you inherently just do? Very good, Martha. Okay, remember, multiply by R squared, divide by FE. Just switch them, really. Just switch them. So we start the problem by doing that. Just like we did with V equals X over T. Remember, when this was V equals X over T, we had these 3 variables, and we were able to switch these 2. We could take our V and our T and switch them diagonally right here. So we did the same thing. Now, obviously, I'm looking for r, not r squared. So what do I do also? Square root it. Square root whatever is there, and you get rid of the square on the r. So our answer for this problem is actually quite simple. It's just the square root of the following. That's your answer right there. Okay, KC, Q1, Q2 over F, all under the square root. For this problem, I think it's easier because you know why? If I plugged in the beginning, well, I plug in all these numbers, then I got to move numbers with scientific notation. It gets really messy, right? If the numbers were easy and this was like 2, 6, 5, 4, sure, plug in. It's nice and quick. But the minute I'm in scientific notation, I think it's easier just to isolate the variable first and then plug in the numbers. Less room for error along the way. Less room for careless or silly mistakes. What do we get for R in this problem? What do we get? Come on, I got 2 people calculating at all times. That's it. What do I get for R? How far apart are they? I know the units already will be in meters because all of my units are SI units right now. So I know that it's going to be given in meters. Others need to try this. Come on, it can't be the same people using their calculator. A lot of you make mistakes on the test on the calculator portion all the time. Check it, check it, check it, check it, check it, check it, check it. Let's go. All right, Tiana, Maddie, or Martha. The race is on. Let's go. Which of the 3? I see the 3 of you typing away. You want to ask the audience or no? Wait, Tiana's almost done. She's got a grin. It looks like she's almost done. Come on. You can do it. Hey, if I'm having trouble with this, I'd probably do the numerator first, hit enter, then divide by 150, hit enter, and then take the square root of the whole answer, you know? Tiana, what do you have? That doesn't look good. You said error. Oh, error's never good. Error's never good. Maddie, what do you have? 1.26. I think it's a little bit off, but you're only a little bit off, so maybe it's a small mistake. Ben, you got something?
I got 0.0282.
Not 0.028. Did you take the square root? Hold on. Ben might have it. Let's see. Square root that number.
What is it? Just that thing? The 0.346?
I don't know. Let's see.
0.168.
Oh.
0.168. Check your work. You made a little mistake.
What did you guys get? Because I got 0.34.
Yeah, I got 0.246.
Yay!
Did you get that in the back? 0.346?
Yeah, it's taking that long.
What are you showing?
Square
root 96, 47, all over 150. Oh, you gotta have parentheses. You gotta have extra parentheses behind when you went there. Uh-oh. Square root of 99, 58, 48, 6, oh, because look, when you type it in, you get another square root to show the whole thing is being square root.
You know you can just do it in segments, right? Like just,
there.
you start off by typing that part, so you get 18, and then you just divide that by 18.
Yeah, you can do parts, in pieces, it's fine. What? No, you can. You could divide it by 150 right then and there. Well, I would, if you want to check, Matt, multiply these 3, hit enter, and divide it by 150, hit enter, and then take the square root of that answer to check. But in reality, guys, this can really be typed in one line, actually, just so you know. It does work. Tiana just did it, and we showed that. Okay? That means, listen, if there's an error, it's because your parentheses, when you hit error, it says either quit or go to. hit go to, and it'll bring you to the error. And it means that you're missing a parenthesis set somewhere. Okay, if you're getting an error, it's your parentheses.
Divide it? No. Oh, I didn't say it.
All right, without any more delay, let's go to the next thing real quick. I would love to get to this next thing so you don't have any more homework. So if you want to bear with me here, let's press on for now. And if you're having trouble with the calculation still, you come see me at some point. So some key ideas before we get on to the next thing. So the next question we're going to do is what 19.3 is from. So everything we've done so far is really 19.2. So this is going to conclude 19.2 right here. And then we'll do one question that involves a little more lengthy math, and that would be from 19.3. So some key points. First, it's a field force. How do you know that? It's acting at a distance. One particle's here, one particle's here. Are they touching? No. So it's a field force just like gravity. Second, it's analogous to gravity in the formula. We showed that already. GMM over R squared, KQQ over R squared. They're really the same thing. Third, the electric force can be repulsive or attractive. Repulsive or attractive, whereas gravitational force can only be attractive since masses are always positive. And last but not least, the electric force is significantly stronger than the gravitational force. Okay, the issue, though, is that gravity affects all objects. The electric force only affects charged objects. Most things around you are neutrally charged. This board, this marker, this railing, the podium, your desk, your calculator, they're all neutrally charged. They don't have any electric charge to them. So the electric force is not as apparent as the gravitational force, although much stronger in magnitude. Those are our four main conclusions. Let's press on to this last example. For the last example to make sense, I need you to draw a situation of what you see here. 3 charged particles are arranged in a line, right? What does that mean they are? What's the word in geometry? If 3 things are in a line, what do you call them? Collinear, right? Collinear? Linear, well, linear just is two dots connected. It's a linear, something that's linear. Collinear are 3 or more things that are all in a line. An example in baseball, if somebody's making a cutoff throw from the outfield, all of the people are lined up. It's the direct line. You have the shortstop, you have the outfielder, and maybe the catcher who's going to the plate, or the third baseman, depending on where you're going. But they're always lined up because it's the shortest distance. Collinear here is what we have. So we've got particle 1. Particle 1 is located 0.3 meters to the left of particle 2. So far I've got that. Particle 1 is to the left of particle 2, which itself is to the left of particle 3. So here's particle 3 all the way on the far right. Well, how far apart are they? This first one says that this is 0.3 meters away. The next one says is 0.2 meters away. So let's go over this diagram because I find that this could be the most difficult part for some students. It's coming up with the scenario that they've got. Again, 3 charged particles in a line. Particle 1 is 0.3 meters to the left of particle 2. Well, look at this part of the diagram. That demonstrates that perfectly. Particle 1 is 0.3 meters to the left of particle 2, which is, meaning which itself, particle 2, which is 0.2 meters to the left of particle 3. Well, how far is it? It's to the left of particle 3 by 0.2 meters. So that's physically what we have here in this setup. Now, let's jot down our charges. Q1. And don't write it in expanded form. Leave it with scientific, with the abbreviation for now, with the prefix for now. Particle 1's charge is negative. Particle 2's charge is positive. And particle 3's charge is negative. Before I get to the last part of this question that we have to really identify, I want you to pause for a second and make believe that you're particle 1. So Eric is particle 1, Maddie is particle 2, and Nico is particle 3. Alright, so Eric, you're particle 1, you're hanging out over here, and Maddie's this positive force, and you're a negative force. or now Maddie's a positive charge, really. You're a negative charge. So what are you going to feel as a result of that?
I'm attracted to that.
Yeah, you're going to be attracted. You like to set that up? I got you there. I'm just messing up. So you feel that first force is attractive. I didn't mean this in male-female way at all. It's just the way it worked, by the way. So then, obviously, an ego on the far end is a negative charge. He's a negative charge. Eric is a negative charge. So as a result, there's a feeling of repulsion of two negative charges. So if you identify, all right, it was kind of funny, but let's relax now. If we take a look specifically at that first particle, which is where Eric was, Eric feels the pull from particle 2, but he feels a push away from particle 3. Is that clear what's physically happening there? Now, Maddie in the middle, this is a great one, here we go. Maddie is this positive charge in the middle, but she's surrounded by two negative charges, so she's being pulled which way? In both directions. Maddie's like, who's going to pull me harder? Which one's pulling which way, right? Every tug of war? Okay? So the middle charge alone would feel pull in both directions. Whichever was greater would indicate which way the middle charge would then move. And finally, the third charge would be similar to the first charge. Because if an ego over here was a negative charge, that would be pulled to the middle because of Maddie's positive charge, or repelled back because of Eric's negative charge. So each of these particles feels something different. Is that clear? Everything feels something different based on the signs. Which particle are we interested in this problem? Particle 3. In this case, that was an ego. Yeah. 1 and 3, though, are very similar. But particle 3 is what we're concerned with. So please go ahead and draw. Please draw just particle 3. We're going to draw a, what do you think? What kind of a diagram? Yeah, free body diagram. Because this can demonstrate to us what's physically happening here. So, particle 3. This was an ego over here. An ego's a negative charge. Maddie's a positive charge. Maddie's saying, come on, an ego, come over here. Help me out a little bit. She's pulling on him to come over because she's a positive charge and he's a negative. So he feels a pull toward the second charge because of Maddie. That's a pull on particle 3 from particle 2. I want to explain the subscripts. Again, an ego feels a pull. The pull is a force on particle 3 from particle 2. That's why it's F32. We're going to give subscripts here with numbers now instead of letters. It is an electric force, absolutely, but it's an electric force on particle 3 from particle 2. Now, Eric on the other side over here, Eric's his negative charge, so he's pushing an ego away. He's saying, no, go back that way, I'm pushing you away. So he's pushing Q3 to the right. So as a result, there's a push to the right, and that's a push on particle 3 from the first particle. Again, the first particle is saying, I'm negative, you're negative, I'm going to push you that way, so there's a push to the right. The question is, which force is really greater here? And then we'll know which way an ego, or particle 3 in this case, will move. Which force is greater? Determine the net electrostatic force. Net. What does net mean? What does net mean to you?
It's like total.
Total. Very good. So if one is pulling to the right, we call that force positive. And to the left?
Negative.
Okay, so all we're going to do at the end is find out both forces. F32 and F31. So it's going to take a little bit of math here to do that. So between particles 3 and 2, let's start with that one. We've got KC, Q2, Q3 over R23 squared. Take a look at my formula, please, before you go any further. I called it 3-2, but I don't care what the subscripts are over here. They really don't matter, right? But R23 is the distance between objects 2 and 3. Q2 is charge on object 2. Q3 is charge on object 3. The subscripts of the force that you're looking for indicate what you're going to use in the formula, bless you, itself. So we go ahead and plug in. 9 times 10 to the 9. Particle 2 is 3 times 10 to the negative 6 coulombs. Now, this is the only time where we're going to ignore the negative sign for Q. We're going to ignore the negative sign for the Q value because you already took it into account with your free body diagram. The free body diagram takes into account whether it's a repulsive or attractive force. So there's no necessity to put a double negative and then you'd be kind of countermanding what you did earlier. You'd be contradicting it in a sense or taking it back. So this Q3 is just going to be 4 times 10 to the negative 6. Again, where am I getting 10 to the negative 6? This micro symbol that's in all of these above. Micro means 10 to the negative 6. But what I'm trying to explain to you here is that you don't need a negative sign for Q anymore when we have 3 particles. You don't use one. You're not going to use one. Write yourself a little note. You're not going to use the negative sign in the front for the 3 or the 4 or the 8 in these problems anymore when we have 3 particles. Then we take a look at how far apart are particle 2 and 3. It looks like they're 0.2 meters apart. Looks like they're 0.2 meters apart. I'm going to get a number. I'm going to leave that for a moment. I really don't care what the number is right now. I'm then going to do the same thing for F31. It's literally the same formula except with new subscripts. Q1 is there now instead of Q2. Q3 is still there, but R13 is different also. So the first part is the same. Now we've got Q1. And then we've got Q3 still. Again, notice I'm not including the negative sign for Q1 or Q3. We already took into account that it's a repulsive force with the free body diagram. And what's the distance between particle 1 and particle 3? 0.5. And if it's not obvious, simply go back and take a look at the diagram. The distance from here to here in the diagram is 0.5. We're going from the beginning to the end, so sum together these two numbers up here to give you the overall distance between them. Numbers, numbers, numbers. Numbers, numbers, numbers. Go ahead, give me one of them. 2 is what? 2.7, I agree. The second number. The second number. Come on, Martha, you got this one. Let's go. The second number. Let's save it. Come on, before the Angie, go. 1 point. Good. I'm going to round it to 1.2 for now. Please take a look up at this point, even if you start calculating. Look up. Look up. The bell's going to ring. I don't want you to lose this. Now, listen to the last part. We got one big conclusion to make. Please don't pack up, guys. It's the end of the day. There's no reason to be in a rush. It looks to me like the pull to the left is stronger than the pull to the right. The blue at the bottom right here is F31. That's the pull to the right. That's this from the bottom. But the pull to the left is 2.7. So if I look at this problem, I think of this as a tug of war. I'm being pulled to the left with 2.7. That's negative. I'm being pulled to the right with 1.2. That's positive. So the overall force, since the negative is more, would be negative or to the left. So what's the net electrostatic force on this particle? Negative 1.5 newtons, meaning that particle 3, will move to the left, or will get pulled to the left. Okay? Hey, to give you a little extension, this is like part A of a 5-part problem in an AP Physics course where you then go on to figure out, all right, well, what's the overall acceleration? You have F equals ma. If you get the mass of these particles, you find the acceleration. From the acceleration, you can find the distance traveled in a given time period. From the distance traveled in a given time period, you can find the work done or the power generated. From the power generated, you can then conduct how much electricity you get as a result. So there's like 6 more steps to this. This is like the very beginning of a problem you could imagine. Okay, but again, a problem that is from 1903 a little bit trickier than 19.2, but not impossible. Over the weekend, tonight, you have 19.2 problems, rather straightforward. You have one problem like this. Do not give up just from the diagram. I need to see that you do this. So tonight, you're going to practice a problem that looks very much like this. It says 3 particles are on the x-axis. So literally just draw an x-axis and put them on the axis itself. Okay? Have a good day, guys. Maddie, I saw your email, but I did not even get out of a meeting. I was